All right, so welcome back, everyone. So we're very happy to have the third talk for today, given by Dimitrios Tsimpis from Lyon on universal accelerating cosmologies from 10D supergravity.
Thank you very much, and thanks to the organizers for the wonderful hospitality. So I'm going to be talking about a paper that appeared very recently that we wrote with my student, Paul Macronet. And yeah, let me walk you through the motivation. Now, as you all know, there's been a lot of effort recently and not so recently in trying to obtain realistic cosmologies coming directly in a top-down approach, coming directly from the low energy effective actions, effective supergravities that we get from string theory, from superstring theory, or M theory. Now, as most of you know, at the end of last century, beginning of this century, it was thought that accelerated cosmologies were just as hard to obtain in this context, in the context of the low energy effective actions of string theory or M theory, as it is to get de Sitter space. And that was due to the famous no-go theorem, first pointed out by Gibbons in the 80s, and then rediscovered much later, about 20 years later almost, by Maldacena Nunes in the context of superstring theory and M theory, and also generalized by Maldacena Nunes to the massive 2A supergravity. Now this no-go excludes, in its most general version, excludes accelerated cosmologies under certain conditions. And these conditions are the absence of exotic objects like sources, localized or otherwise, or singularities, although in the Maldacena Nunes it was pointed out that certain singularities could be allowed. It assumes compactness, and it assumes we're working with two derivative supergravities, and so no higher order corrections. And it assumes that the strong energy condition is obeyed in the higher dimensional theory, so in 10 or 11 dimensions, although that might not be obeyed in the lower dimensional theory upon compactification. Now, just to remind you how this goes, let's suppose that we have a 10-dimensional or 11-dimensional higher dimensional space, which is of this warped form, where omega is a warp factor, as is commonly known, that depends only on the internal direction. So here, Mn are the internal directions. For us, they would be parameterizing a 6 or a 7-dimensional space. And x mu would be the external space-time directions, and for us that would be 4-dimensional space. And yeah, crucially, the warp factor only depends on the y, the y internal directions. Now, suppose that the 4D external space is of a Friedman, Lemaitre, Robertson, Walker form, where T here, capital T is the cosmological time, S is the scale factor, and gamma ij are the space, 3D space directions, and they are normalized in this way, where k can be negative, 0, or positive for hyperbolic, flat, or closed space. And in this case, we can calculate the tensor of the higher dimensional space and relate it to the one in the lower 4D dimensions, and we get a contribution from the War factor. Now, the strong energy condition in the higher dimensional theory, so the hatted objects are objects in the higher dimensional theory, means this condition, which is related to the stress energy tensor of the theory in the higher dimensions via the Einstein equations, and imposes that. And then a little bit of calculation, integration by parts over the internal space to get rid of the omega contribution will boil down to this condition, excluding acceleration and for the cosmology. Now, it was pointed out a little bit later by Townsend and Wolfart that that no-go, and this is surprisingly perhaps something people may not always realize, that this no-go can be easily bypassed by allowing the War factor and also the internal metric to depend on the cosmological time, on the 4D time. And in fact, Townsend and Wolfart pointed it out by construction that there are indeed accelerating cosmologies that can be obtained in this way, sidestepping the no-go. And shortly afterwards, there was a flurry of work on this that showed that actually transient acceleration, accelerated expansion, is, one can say, generic in flux compactification. So there's no particular difficulty in coming up with such examples in flux compactifications. Now, even with this relaxation of the no-go, so I remind you this consists in allowing a time dependence on the warp factor and the metric, and also all the scalar fields can be time dependent. This will not violate the Friedmann-Lemaitre-Robertson-Walker isometries. Even if one allows that, it turns out that de Sitter space is still ruled out if one insists on imposing the strong energy condition. However, as Russo and Townsend pointed out relatively recently, so Russo and Townsend improved quite considerably on the no-go, and one of the things they pointed out is that one may even have de Sitter space if one allows for the 4D Newton's constant to be time independent in the conventional and the non-conventional sense. But if one insists on the 4D Newton's constant being constant in the conventional non-averaged way, then de Sitter space is still ruled out, even if one allows this. Now, one thing that's not excluded is late time acceleration. And by that I mean acceleration that starts at some point and never stops. However, all the known examples of this that we find from flux compactifications are such that the acceleration tends to zero at future infinity. This is just an observation. At this point, there's no particular reason, as far as I know, that this should happen, and indeed the updated no-go does allow for, it would seem, for it. Now, our motivation was to re-examine all these statements within what I would like to call universal compactifications of 10D or 11D supergravity. And by universal, I mean that model independent, in the sense that I will consider certain wide classes of compactifications on 6-dimensional manifolds. So we worked mostly with type 2A supergravity. We also have some solutions of type 2B. But the paper is mostly concentrated on type 2A, and that, of course, is liftable to, so all the solutions that we find will lift to 11-dimension supergravity as well, if they don't have a non-vanishing Raman's mass, and there's a lot of solutions that do not have non-zero Raman's mass that we find, and I will talk about that. So universal in the sense that compactification classes that we consider will not be taking into account the particulars, the particular details of the compactification class I consider. For example, if I talk about Calabi-Yau compactifications, I will only assume the existence of a Keller form, of holomorphic 3 form. I will not assume that there are any non-vanishing 2,1 harmonic forms, for example. So the models I consider will be always there for whatever Calabi-Yau you consider. Yes?
From a physical point of view, these time-dependent reductions, the couplings are going to be time-dependent.
Yes. Yes, of course. So in general, the solutions that I will present also will have this feature. There are some that for which the dilaton is constant, but yeah, in general, there will be time dependence. So as a general remark, I should say perhaps already that our motivation was not to obtain necessarily realistic cosmology. The motivation was to see what kinds of models we do get from those low energy supergravities. What are the generic models, the ones that do not depend on the details of of each compactification, and what are the general features of those models, and whether or not what I will be talking about could be used for realistic cosmologies or work towards building realistic cosmological models, it's an open question. I think, well, I'll try to convince you that we find some interesting phenomena that have not been observed before that might indeed be part of the realistic cosmology. But that was not our motivation, and certainly do not claim that we're trying to do realistic cosmology here. Just to see, be open about it and see what we get from those supergravities.
From a 3D point of view, your scalars are also time dependent, so they will have large excursions in one flat space. Is that a problem?
So in the as you will see shortly, the models that I will be talking about only have 3 scalars, the dilaton and 2 warp factors, and all the other fluxes will be just reduced to constants by virtue of the ansatz that I will consider. You will see that in more detail in a minute. So yeah, of course one could ask what the time dependence of the different scalars are, and there are different qualitative behaviors that will be present. Now, so Yeah, so we'll be considering generic compactifications on 6-dimensional Einstein-Keller or Calabi-Yau spaces. The solutions that I will be presenting will be independent of the details of those spaces, but will always be present whenever you have a Calabi-Yau. So no matter what the Calabi-Yau is, the compactifications on it that I will be showing will be valid by construction. So as it turns out, all the solutions that we obtain are obtainable from a one-dimensional action. In other words, there is a consistent truncation and to one dimension, and this consistent truncation has three scalars, which will be time dependent. As I was just saying, the dilaton and the two warp factors. And all the flux of my compactification will appear as constants of a certain potential, of the potential of that consistent truncation. And in certain special cases, but not always, there's also a 4D consistent truncation to two scalars, but that's not always the case. So I just remind you, here I'm using consistent truncation in the technical sense that all solutions of the lower dimensional theory will lift to the to solutions of the higher dimensional theory. Yes?
How many supersymmetries survive in 4 dimensions?
Here is 0. I'm only considering the bosons. But I'm expecting these to be, well, the solutions are not necessarily supersymmetric, but the theory, of course, that we work with is supersymmetric.
By scalars, you mean real scalars?
Yeah, real scalars. Mm-hmm. Now, we do find a host of analytic solutions. This is always possible if, besides the three scalars I'm talking about, you only excite a single species of flux. But it also accidentally happens in other cases. So, if you have more than one excited species of flux, you are not guaranteed to be able to find an analytic solution, but it may happen that you stumble on some analytic solution even when several excited fluxes are turned on, and we do find a lot of examples with some up to 4 different species of flux. So there's quite a rich variety of analytic solutions that we find. Now, if there's more than one species of flux that is turned on, as I said, it's not guaranteed for there to be a analytic solution, but in this case, there's also something nice you can do. And it turns out that there's a description of the system as an autonomous dynamical system. And this description allows you a very intuitive understanding of what's happening. So the cosmologies, the solutions, will correspond to trajectories in a certain phase space, in a 3-dimensional phase space, subject to a certain constraint, which I'll talk about in detail. And in this description, as we will see, the question of accelerated expansion, whether or not there is accelerated expansion in a certain solution, will become very intuitive and will be obvious whether or not there is expansion. Now, the fixed points in this phase space, if they exist, will correspond to scaling cosmologies. So cosmologies where the scale factor is the power of the cosmological time. And also, so they can be constructed analytically. And this is also the case for trajectories that lie on the boundary of the phase space. Now, what we find, so as I was saying, our motivation initially was to try to have a repertoire of what kinds of cosmologies we get from those higher dimensional supergravities in a systematic way, in a model-independent way. But we were not expecting necessarily to find new qualitative behaviors. But there we had some pleasant surprises. Namely, we find a lot of examples of cosmologies where there is a parametric control of the number of e-foldings. So you can tune a parameter and increase to, at will, the number of e-foldings that you get in this cosmology. There are examples of semi-eternal or eternal inflation, and also there are several examples of what has been called recently roller coaster cosmology, namely where you have an infinite cycle, an infinite number of cycles of accelerated and decelerated, followed by decelerated expansion. So careful here. I'm not talking about expansion and contraction, but cycles of acceleration and deceleration, and while being constantly expanding. So these are interesting features that can be constructed by hand in an ad hoc way. Let's say from a 4D perspective, the bottom up. But to our knowledge, this is the first time this has been observed as part of a model that comes from compactification of 10 or 11 dimensional supergravity. So let me get to some of the details. So the starting point will be the type 2A, let's say, supergravity, where phi is the dilaton, F is the 2 form, H is the Navier-Schwarz 3 form, G is the 4 form, and M is the Romans mass. And M, again, I stress that can be non-zero or can be zero. It doesn't have to be non-zero. I'm not only looking at massive 2A. Indeed, M will be zero in most of the solutions. The ansatz includes two warp factors, A and B. Here, so this is just to set up the conventions. T is the conformal time. D omega is the 3D line element, and has been normalized in the same way that I mentioned before. Tau will be the time of my 1D, it's the preferred time in which the 1D consistent truncation is best described. S is the scale factor, and capital T will be the cosmological time. So let me give you some examples of flux Ansätze, just to justify what I mentioned briefly earlier, that in my description, the fluxes will appear as constants. So the Ansätze for the fluxes are constructed in purpose in such a way that they automatically solve their Bianchi identities and the equations of motion. So we don't have to deal with them ever again. And here are some examples. One possibility for Calabi-Yau is to set the Romance mass to 0, the 2 form to 0. The H form will have a 3 form part that is along the space-time dimensions, and a 3 form part that is along mixed directions. J is the Keller form of the Calabi-Yau, omega is the holomorphic 3 form, and this B0 is a constant. The 4 form similarly will have a 4D space-time piece with some scalar phi. C0 is a constant, and this part will be mixed. We'll have 3 legs along the internal directions and 1 along 4D space-time, and eventually I will just allow for time dependence in order to respect the Friedman, Lemaitre, Burton, Walker isometry. So this will be only time dependent. So this will be time and internal mixed components. And if you take this ansatz and you impose the Bianchi identities and form equations, you find that they are solved provided these relations hold. And so you end up parametrizing all your fluxes in terms of these constants that appear here in red. So that's the end of the story for the forms, for the form equations of motion and Bianchi identities. And now we can concentrate on the remaining equations of motion, the dilaton and the Einstein equations. And there's a similar story for the other classes of compactification, and that's not the whole set of possibilities. That's why I'm saying here examples. There are different types of fluxes you can turn on, and so on and so forth. So there's several possibilities that are consistent and that work in the same way, namely the ansatz for the fluxes solves the equations of motion for the fluxes and their Bianchi identities and reduces to a parametrization in terms of only a set of constants. When I started,
I think you started 4:45. 4:45.
4:45. Oh, okay, great. So as I was saying, there's a one-dimensional consistent truncation that can be seen as follows. So the having dealt with the form equations of motion and Bianchi identities, we list the remaining equations of motion, and these are the internal Einstein equations. The B equation of motion comes from the external Einstein equations, and there's the dilaton equation, and they all can be written in this form. It just turns out that they are of this form, where U is a function of A, B, and phi that I call a potential, and will play a role of a potential in the consistent truncation. So at first, you write down the equations of motion, and you find that they can be written in this form, subject to a constraint that also comes from the external. So these two, in fact, are both coming from the external Einstein equations, and I have taken a particular linear combination to put them in this form. Yes.
TT is just
Yeah, exactly. Yeah. Now, as it turns out, this set of equations is integrable into an action, which is not guaranteed, of course. And this action is of this form. So we do have a consistent truncation, and it looks like this, where n is a Lagrange multiplier, and u depends on the class of compactification that one considers. So here I have listed U in all different cases. And in some cases, there are different possibilities for the fluxes that can be turned on consistently. So we sometimes have two possibilities for the same class of compactification. For example, here in the Calabi-Yau, or we can have three different possibilities for the Einstein-Keller compactification. So this comes about because we cannot always solve the Yankee identities and form equations of motion in a consistent way unless we set some of the fluxes to zero. This is part of the limitation that I impose that the flux equations of motion and Yankee identities are dealt with once and for all, and the remaining, the resulting consistent truncation only depends on the fluxes through these constants that you see here, and otherwise is a functional of only three scalars and a metric. So it's a consistent truncation of the higher dimensional theory to three scalars and one metric, but it knows about a host of different fluxes coming from the higher dimensional theory. Indeed, if you wanted to uplift it to the higher dimensional theory, you would have to go back and reconstruct your fluxes in this way. Okay, so this is a reminder of the higher dimensional origin of the different constants. So in particular, yeah, lambda would be the internal curvature of the internal space, the compactification space. So that would be relevant in Einstein compactifications. And K is the external 3D curvature. And we have a bunch of constants that correspond to these higher dimensional fluxes, where, for example, CF is internal 2 form, CH internal 3 form, and so on and so forth. So in the paper, when we talk about fluxes, we talk about fluxes in this loose way that includes also the curvature, because it's more convenient, because the potential does not distinguish between flux contribution and curvature contribution. They all come in this form of exponential. So each flux will contribute an exponential of this type, and the coefficients alpha, beta, gamma are given by these formulae, where nt is the number of legs that a form has along the time direction. So in that case, it's either 0 or 1. ns is the number of legs along the 3D space, and ni is the legs along the internal space. And well, for ns and s forms, gamma is just -1 to the nt, I think, maybe with -1 in front. Now, there's one very simple solution, the simplest solution when there's no flux. So in this case, the potential is 0. Now in this case, we just have linear functions for a, b, and phi, and there's a quadratic equation, which is the constraint that constrains these constants, the slopes of the linear functions. This is what the constraint is saying. And in that case, what we get is a scaling solution with a factor 1/1/3 for the scale factor. So this remember, this is just s squared, the scale factor. And we can have internal space that decompactifies or collapses or stays constant depending on the values of Ca, Cb, and Cf, C phi. All possibilities are present. And we can also have a constant dilaton whenever these inequalities are saturated. Now, as I said, it's not always guaranteed that there will be a 4D consistent truncation. This is possible in only these 4 cases that are listed here. And in this case, the 4D consistent truncation will be a truncation to 2 scalars and a metric. Now, I seize the opportunity to mention something that maybe it's not widely appreciated, but in the Calabi-Yau case, in the universal sector, so precisely the same situation that I've been talking about here, so where you have one hypermultiplet, one vector multiplet, and the metric multiplet, the effective action of the Calabi-Yau compactification is actually a consistent truncation. And in general, it is not believed to be the case, but it so happens that the universal truncation, the effective action, the universal sector of the effective action does happen to be a consistent truncation of the 10-dimensional theory. And in that case, I would expect this consistent truncation to be part of course, part of the effective action. But in general, consistent truncation and effective action are not the same thing, and one in general would not be guaranteed that the consistent truncation is a subsector of the effective action. But in our case, where the consistent truncation is universal, is a universal truncation, I would expect it to be indeed part of the effective action, at least for some parameter of the moduli space. Some subspace of the parameters. Now, as I said, when we have 2 fluxes turned on, so the potential is a linear, consists of 2 exponentials, a sum of 2 exponentials. In this case, it turns out we can rewrite the system of equations and the constraint that we saw just a minute ago. After suitably choosing a different parameter for the dynamical system, we can write it in this way. So, autonomous dynamical system subject to a constraint. And even better, we can use a different set of variables that I've listed here after this change of variables that is inspired by Sonner and Townsend. We can rewrite the system in an alternative way, which has a certain advantage that I will point out in a second. And of course, we can keep track of the different flow parameters along the way. And the advantage of this rewriting is that when you write down the constraint in the new variables, what you realize is that it forces the flow, the trajectories in phase space to lie either in the exterior or in the interior of the unit sphere. So now the phase space is parameterized by x, y, and z. C1, C2 are just two constants that are related to the fluxes and that enter the potential. Furthermore, probably won't have time to explain that in detail, but as it turns out, all the interesting cases is when first of all, the constants are usually positive, and when there's an option that they are not, which only happens when these constants represent curvature, then there's not much going on outside the unit sphere. So for all practical purposes, we can concentrate on the case where the constraint just tells you that we are in the interior of the unit sphere. Now, a little bit of a manipulation of the system reveals that the unit sphere itself, so the boundary of the unit ball, is an invariant surface. So you can, as you can see, the derivative of this combination brings a factor of the equation of the sphere. So if a trajectory touches the sphere at one point, it will remain on the sphere forever. And the constraint also guarantees that it will remain on either side of the sphere if it starts out there and can only approach it asymptotically. And similarly, there is another invariant surface, which is the equatorial disk. So the surface z equals 0, and that's even simpler to see. You can see that directly from the last equation here. If z is 0, it will remain 0 forever. And of course, the intersection of these two is also a fixed surface, and as it turns out, it is a circle of fixed points. In fact, more than just a fixed line, fixed circle. It is a circle of fixed points. There are infinitely many fixed points on this equator. And it also turns out that there is always an invariant plane in the phase space. Given by this equation, where the orientation of the plane is entirely dependent on the fluxes you consider. So the alpha, beta, gamma, which in their turn depend on the species of flux that is turned on. Now, what is also very nice about this description is that the condition for expansion, after a little bit of calculation, turns out to be equivalent to this condition. So it just tells us that you have to be on the northern hemisphere. Another feature is that the trajectories on the northern hemisphere are paired with trajectories on the southern hemisphere. So again, we can concentrate on, say, trajectories in the northern hemisphere, which is also what we're interested in because that represents expanding cosmologies. Now, the question of acceleration can also be reformulated in a very nice, intuitive way, and boils down to an existence of a certain acceleration region. So there will be acceleration whenever we have this equation to hold, which means that the trajectory must lie within a certain geometrical region, which depends on the two fluxes that are excited. So it depends on the coefficients beta 1, beta 2. And there can be different shapes of the acceleration region, but whatever it is, it's very easy to visualize. I will give some examples. Okay, let me complete all the nice features of this dynamical system by saying that the parameter flow, so remember after all our rewritings and so on and so forth, we ended up with the flow parameter for our phase-space trajectories, omega. Now, this omega that we chose in that way turns out to be essentially the logarithm of the scale factor. So in particular, if you're interested in computing the number of V-foldings, you just have to calculate the length of the trajectory, essentially. And if you, again, followed the different redefinitions that we did to arrive here, you can also see that the cosmological time is related to the flow parameter in this way, meaning that we can calculate it. We can calculate it numerically. So it's an integral that's easy to obtain numerically, and this can be inverted to give us the scale factor. Since omega is just the logarithm of the scale factor, this can be used to give us the scale factor as a function of the cosmological time. So that would be the data, that cosmological datum that you're probably most interested in. But of course, if you know the scale factor as a function of the cosmological time, you can also compute anything else you might wish to compute, such as eta, Hubble constant, Hubble parameter, etc. So let me recapitulate. So we have lots of analytical solutions that we list, but that's not systematically possible to do in every case. However, there's a nice playground of solutions that is very rich, and that includes two excited species of flux. In this case, you have at your disposal a dynamical system description in terms of trajectories inside the unit, the northern hemisphere of the unit sphere, And cosmologies will correspond to trajectories in this space. Now we have the boundaries of this space, namely the dome of the northern hemisphere and the floor, the equatorial disk, are fixed surfaces. And whenever we have trajectories that lie entirely on them, we do have an analytical solution. And similarly, there is a plane that is a fixed surface, and we have a circle of fixed points that are on the equator. And whenever we have a fixed point, we have an analytical solution, and this analytical solution is a scaling solution, so the scale factor is the power of the cosmological time. Rephrasing the question of accelerated expansion becomes very visual now. It says that expanding cosmologies should correspond to trajectories in the northern hemisphere that pass from the acceleration region, whenever this exists. And it's not hard for it to exist. So as we saw, there are a lot of cases where it does exist. So whenever there is such an acceleration region, we can always pick a point within this acceleration region. So here, this is an acceleration region. It's just z greater or equal to something, some altitude. Here, it suffices to pick a point in here and consider a trajectory that passes the trajectory that passes from that point. That trajectory will always exist, and it will correspond to a solution with transient, in general, accelerated expansion. So here's an example that is from the paper. We have a trajectory that starts and ends on the equator. So this means, by the way, I'm not sure if I mentioned it, but the equator points all correspond to the scaling solutions of the simplest type that I mentioned at the very beginning, so t to the 1/3 for the scale factor. So at past infinity and future infinity, you have a scaling cosmology of this type. Then there is some expansion happening. You enter the acceleration region, and then you start an accelerated phase. And at some point, you will exit, and that ends the acceleration. And then at future infinity, you end up with a scaling cosmology of t to the 1/3 again. And the number of foldings is the length of the total length of the flow parameter for this part of the trajectory. So that explains why this observation that was made in the beginning of 2000s, that it's easy to find acceleration, transient acceleration, accelerated expansion, and flux compactification. Here we see why. I mean, there's infinite number of accelerated trajectories that pass from this acceleration region, and it just suffices for there to be an acceleration region, which is easy to accomplish. And once you have that, you are guaranteed to have an infinite number of accelerated expanding cosmologies. Yeah, so I was saying fixed points correspond to scaling cosmologies of this type. The equator is a particular kind of such a scaling solution. And we do find other types of scaling solutions. we find scaling solutions with A equals 1. These correspond to Milne universes that can be either regular or singular. They are regular if they happen to be at the origin, and they are singular otherwise. And there are other fixed points with A equals that we find, that there are 3/4 this funky power and 9/11. And in no case is there any eternally accelerating scaling cosmology. So we never find A higher than 1. So here's an example. I think this is the case where we have a non-zero Romance mass and non-zero internal curvature. There's a fixed point here that corresponds exactly to this 3/4. There's another fixed point here, that's the 19/25. And we have some transient acceleration. The trajectory exits at some point and reaches a fixed point at a future infinity with a scaling of 19/25. And at past infinity, it had a scaling of t to the 1/3. Now, so far, those examples are not new. It was known that you can have that kind of behavior, but here is some new results that were at least surprising to me, and whose occurrence was found for the first time in this paper in the top bottom approach. Of course, you can construct such models by hand in 4D, but these come from 10 or 11 dimensions, so they are highly constrained. Here is an example where there is an attractor point, so the end point of the trajectory is an attractor point which lies on the acceleration region, which is a cone here. It just so happens. So this example is I think is the MK, no? Is the MK example, but all the examples where you have K hyperbolic, and one of these types of fluxes turned on will have a similar qualitative behavior. So I'm just picking one of them to show you an example. And what happens is in the past infinity, you have the usual scaling solution with t to the 1/3. You have some transient acceleration, but then at future infinity, the trajectory spirals around a fixed point, which is at the acceleration region, at the boundary of the acceleration region, corresponding to a Milne singular space. And what happens is here is not seen very well, but you have a spiral of infinite cycles where the trajectory exits and enters the cone. So you have an infinite number of cycles with acceleration and deceleration. But you always have expansion because you're in the northern hemisphere, so remember. So that's a roller coaster example, and each phase of acceleration will contribute a fixed number of e-foldings, and the number of e-foldings tends to infinity in this case. Here's another example of eternal and semi-internal inflation, and an example of the semi-eternal inflation is this red trajectory. So you have, and here I'm confined to the invariant plane of the phase space. So this is trajectory that lies on the invariant. These are trajectories that lie on the invariant plane of this phase space. So this is a semi-eternal. It starts at past infinity with a scaling solution of t to the 1/3. There is some expansion. It enters the acceleration region in green, the cone. So here we have expansion, and asymptotically it will reach that point, attractor point, which happens to be on the acceleration region boundary and corresponds to a Milne singular universe, and will never exit the acceleration region, so it's a semi-eternally accelerating. Now, there is also a unique trajectory, which is this one here in purple, that actually never ever leaves the acceleration region, so it's eternally accelerating, but is contracting at first and expanding at later times. Here at the origin, one can calculate explicitly, analytically, the scale factor to any given order in the cosmological time in a perturbative Taylor expansion. And you find that it's de Sitter in hyperbolic slicing, at least up to order t to the 3rd. So the scale factor is that of de Sitter in hyperbolic slicing. So it's yeah, exactly. So you have de Sitter's sine hyperbolic scale factor, and that is of this form up to and including t to the 3rd. Now this here I zoomed in on the spiraling solution a little bit. You can see a little bit better the spiraling, but again, since the radius around the attractor point diminishes exponentially, it's very hard to show you a picture that will be better than this. And you can see here we have expansion, we have acceleration, here we have deceleration, here we have acceleration, deceleration, and so on. And in this type of cosmology and of solution, we also have a unique trajectory that is the analog of this one in purple, with the difference being that at future infinity we have this roller coaster behavior. And the unique trajectory again is without Big Bang singularity. At the origin we have again de Sitter space. This is not asymptotic de Sitter space, but it is smooth and there's no Big Bang singularity. So let me conclude. So we confirmed in this paper that in a large and generic model independent or universal, if you will, type of top-down flux compactification, there is generically transient acceleration. We found several examples, so that I think it's a novel observation that feature phenomena that go beyond that, namely semi-eternal acceleration, parametric control of the number of V foldings, and this spiraling, this roller coaster behavior that is also generic. We found an abundance of such instances. That doesn't seem to be difficult to construct. In all the instances thereof, you have to have hyperbolic 3D space. So that's a feature of all the examples that have these behaviors. And asymptotically, you do find vanishing acceleration because asymptotically you tend to Milne universe where the scale factor goes like t to the 1. Now, there are a few open questions that we would like to address. For example, there's been a lot of work on coming from the 4D effective approach, and a lot of swampland conjectures associated with this. Now, in principle, you could compare with those and the various no-goes or conjectures that have been formulated. At least in the case where we have a 4D consistent truncation. So at least in this case, you could easily compare with various conjectures, which are usually based on a 4D potential. And one limitation of what I've been showing is the fact that you must have up to for the dynamical system description to be nice and simple and have all these nice features. You have to have 2 fluxes turned on. If you the moment you turn on the 3rd flux, well, you can still force the system to be. Well, you could still write it down and try to describe it as a dynamical system, but it's not so intuitive or so useful anymore. So it'd be nice to know if there's a clever way to go beyond this limitation, which seems artificial. And indeed, there seems to be a much richer phase space with the possibility to turn on lots of different fluxes at the same time. So it would be nice to be able to explore more of this phase space. And so what I did here is like really minimal supergravity without 2 derivatives, with no sources or higher derivatives. Of course, one could try to go beyond that and include derivative corrections and sources, in particular orientifolds, and see how this affects the discussion. And we had some discussion on this at the beginning. Of course, it would be nice to know if some of what I've been talking about could be relevant for building realistic cosmology models coming from 10 or 11 dimensional supergravity. Of course, that would be the hope, and but at least I think we have enough of a rich system and tools that I think we can make a step towards this question as well. So, thank you.
Further questions for Dimitrios?
You've been mentioning about the effective 4-dimensional approach. So in the case of Calabi-Yau, you have got n equal to supergravity. Did you try to obtain your effective 4D model as a truncation of any n equal to supergravity gauge?
Yes, that's about what I mentioned. In fact, recently, we realized something that is not widely appreciated, I think, that the n equals to 4D supergravity that you get from Calabi-Yau.
Yeah.
So this is this reference here. if you truncate it to the universal sector, you can show that it's a consistent truncation.
What do you mean by universal sector?
One hypermultiplet
Okay.
and one vector multiplet and the metric multiplet.
The one vector multiplet, so you have to specify in general the prepotential of the geometry of the.
Well, these
Scarlet
are all the fields that come from the reduction. If you set h21 to h21 to 0 and h11 to 1.
Okay, so you've got a universal hypermultiplet and a dilaton.
Exactly.
Essentially, but the universal hypermultiplet are 4 real scalars, so you truncate most of them. In order
exactly.
To
So
end
this is indeed a subtruncation of that, in the particular case of Calabi-Yau.
Okay.
But of course, here this one is also available in other contexts, like it's seen here, Einstein, Keller, etc., etc. But something that I also wanted to mention is here. If you take lambda to 0, this becomes also valid on a Calabi-Yau.
You have a potential, so in general, this will mean that you have a gauged n equal 2. So did you try to express that potential as a kind of gauged potential in n equal 2 coming from some gauging of the universal sector?
Yes. This is here. This spelled out in all glory in there, and this is just a sub-sector of that.
Okay.
The problem is that this is just a subtruncation of the full thing, and in general that full thing, the full universal sector with all the multiplet scalars and so on, do not admit this description where the fluxes are just reduced to some constants. That's an extra hypothesis that is fed in here, and this is because of this that we get a sub-sector only.
Okay, I've got another question about the shape of the trajectories. Can you get closed trajectories that end up at the same point that
Like
they start with?
limiting cycles and stuff? No, we don't find any. I don't know. Fortunately or unfortunately, we don't see any exotics such as chaos or limiting cycles or anything like that. We don't see any of that. I don't know if you expand the phase space, if one were able to turn on more fluxes, if that would be possible. I don't know.
Thank you.
Questions?
Hi, thanks. So you mentioned that you have to have k equals -1 to get these sort of eternally inflating models. It seems kind of counterintuitive because one of the points of inflation is it wipes out whatever value of k you have. Is that not?
I've talked to cosmologies, let's say, and they don't seem to think this necessarily would kill the thing as realistic model, but because of course this goes completely out of the standard model of cosmology. So a priori,
after 60 e-foldings, it's not going to matter at all.
Again, so if you take, for example, the roller coaster model, they seem to be able to get away with it with far less e-foldings than this. For example, so it all depends on your premises, and this is not the same starting point as the standard. So I'm not sure that this is phenomenologically a problem.
I'm more worried about mathematically. Like, if you run your clock backwards and you start with your eternally inflating thing at k equals -1, I would have thought k equals -1 has nothing to do with your equations there. So you might as well just put k equals 0 in, and then run your clock backwards.
But no. I mean, for us, we're not trying to explain k, right? So it's part of the ansatz. So in this model, it cannot be. Where is? It cannot be explained because it's set in by hand.
Yeah. That's my point.
But you have omega k in cosmology.
I mean, omega k is not k. It's k divided by
Oh, this is your k is not.
by s squared.
Okay, sorry.
I think you may be talking about that.
Ah, yeah. All right. Your k isn't.
Difference.
Yes. But well, your k is it the k that's either 0, 1, or -1?
Well, here no.
Or is it
Here,
omega
this
k?
This is just, but you can set it to -1 without problem by choosing the initial. You can absorb the actual value of k into the scale factor. So
Right.
there's a constant in the definition. So it's
Sure.
b is a function of time. So there's a constant that is sort of arbitrary there. I can fix this ambiguity by setting k to -1, for example.
Right. Well, maybe we should debate.
But this
that.
is fixed to something. So the important thing is to know if it's negative, positive, or zero.
Okay. I guess I had one other question. Is you might worry that some of these fluxes are constrained to be quantized.
Oh yes. So that we looked into a little bit. It always seems to be enough freedom, at least in the two flux cases, to quantize them, to discretize them.
Even with the running of the cosmology.
Well, these will be discretized by, in the internal space, so without the warp factor. I don't think the warp factor plays any role in this quantization.
Thank you.
Okay, any other questions? If not, let's thank Demetrius for the very